Okay. Good morning, everyone. My name is Aditya Anand. I'm a PhD research scholar at Indian Institute of Technology, Mandi. So, as you see, my title it says Principles of Stage Static plus Dynamic Partial Analysis. So, let me start with my presentation. So, we have several popular languages like Java, C#, Scala, which uses just-in-time compilers. The problem with that is that we can't perform precise program analysis when we have just-in-time compilers because performing compilation at just-in-time is quite inefficient. So due to which most of the JIT compilers perform imprecise program analysis and sacrifice precision for efficiency. So can we use static analysis to improve the precision of JIT analysis? The answer is yes. We have Java source code available at statically, so we can use that Java source code and generate static analysis results and use those results at runtime and can perform more optimization during just-in-time. But there is a challenge. We don't have library code available during static time, due to which most of the static analysis that we can perform will conservatively generate results when we don't have library code available. Since we don't have library code available, we have partial Java program available with us. In 2008, there was a paper titled Enabling Static Analysis for Partial Java Program, which says that we can perform static analysis for the partial Java program which is available to us, which was further applied for the JIT compilers in the paper titled Precise Yet Efficient Framework for Just-in-Time Analysis for Java Programs. So let me first explain how this framework was designed and how it generates precise results even though we don't have library values available at static time. So what Pi framework does is it generates highly precise results for just-in-time compilers at a very low cost. It divides the program analysis in two stages. First, it offloads the expensive analysis to the static compilers and generates something called as conditional values. Further, it uses those conditional values at runtime to evaluate the final analysis result in a more precise way. We can see a conditional values as we can generate conditional values for each program element in such a way that we are denoting dependencies for each program element. Let me give you an example. We can see an example where we have two classes, class A and class L, where class A contains two methods, foo and bar. In class foo, we have three abstract objects, O3, O4, O6, where 3, 4, 6 denotes the line number. At line number 5, we have a method invoked for method bar, where we pass the object O4 pointed to by A2. Similarly, there at line 7, there is a method invoked for library method lib, where also we pass the object O4 pointed to by A2. So if you want to generate conditional values for object O4, Pi-like framework will generate the conditional values something like this. Suppose we have a analysis, we are performing program analysis like escape analysis. So conditional value denoted here for object O4 is a set of several dependencies, where if you see the first dependency, what it says is that the object O4 depends on the first parameter of method bar, and if that parameter evaluates to D, which denotes do not escape, then the overall first dependency for object O4 will resolve to D. Similarly, we have dependency for library, where it depends on the first parameter R1, and the other case as escaping cases. So we have these conditional values which we can resolve to get the precise analysis result. So now we have these conditional values. What we can do is we can evaluate as much as possible statically. So if you see in this method bar, there is no assignment made to parameter P1, which means that is not being assigned to something as global or not being returned from the method bar. So we can conclude that the parameter P1 is not escaping in method bar. So the first dependency, if you see over here, a dot bar P1 can resolve to D. So we can resolve the conditional value as D for that dependency. Similarly, if for the third dependency, since it has resolved to D, the third dependency comes out to be false. So we can take the bottom of the lattice, which will be D again. So we can resolve the third dependency as well as D. On further simplification, we can get the final partial result, in which we can observe that we have dependencies just on the library methods. Since now we have the partial results, can we say that, which still there are some challenges which SPI like staged static plus dynamic analysis do not refer to. For example, is it correct to stage whole program analysis across static and JIT compilation? When we generate partial result, we need an evaluator also, no? So we need, what kind of evaluator do we need at runtime to evaluate those partial results? And can those be generated statically only and efficient as well? Does the precision of staged analysis remain same as the whole program analysis? What about its efficiency? So these are some questions which need to be answered if we are performing staged static plus dynamic analysis. We found that all these questions can be answered if we model this staged static plus JIT analysis to the classic theory of partial evaluation. So let me briefly give you an idea what partial evaluation is and how can we model further the staged static plus dynamic analysis on that. So partial evaluation proposed by Neil Jones in 1966 says that for a given program, first, if we divide the inputs in static and dynamic inputs, we can specialize the program with the statically available input and get a specialized program. That generated program will run or execute faster compared to executing the original program P, provided if we provide static as well as dynamic input altogether. So overall execution time becomes faster. Partial evaluation was also being used to specialize interpreters and their generators based on the notion of Futamura projections. The first Futamura projection said that we can specialize interpreters for the programs by specializing interpreters with the programs written in a language S and get a specialized interpreter. The generated specialized interpreter can take runtime inputs and can give you the final output. This was the first Futamura projection that was given based on the notion of partial evaluation. Further, since we can generate the specialized interpreter for a particular program, we can also generate specialized interpreter in a much efficient way. For that, there were second and third Futamura projection, which says that we can generate their generators in a more efficient way. Yeah. So after this Futamura projection, now let me give you how can we model the partial evaluation based on the same. So we model the partial analysis where the source program from the partial evaluation world, we model that as same as how we model that as a conditional values in our partial analysis world. The static inputs which are required for the which are there for the programs in partial evaluation world, we model them as those conditional values which can be resolved for a given set of conditional values, and there are runtime inputs which can be modeled in the same way how we cannot resolve some of the conditional values. The evaluator or the interpreter which is being used in the partial evaluation, which evaluates the program, we designed a similar conditional value evaluator for a particular analysis, and we map both the evaluators as same. So to model the partial analysis scheme, partial analysis as staged way, we first designed a language for the given conditional values, where if you see we have a program elements and set of we have program elements and set of conditional values, where conditional values can be a class, then method, the type of the object which we have, which can be a local parameter, arguments, return values. The references, the reference which is basically telling that what is the parameter numbers, and the set of fields which an object can have. So this is the language which we model for the conditional values, and the conditional values will look like this after modeling for this grammar. Further, as we said that in partial evaluation, we divide the input in static and dynamic part. So in similar way, we divide our conditional values in static and dynamic way. We divide the conditional values and made a new conditional value, which we call as tagged conditional values. And for the language for that conditional value will look like this, where we have static and dynamic appended before the conditional values. Further, for the evaluator, we have an evaluator which can evaluate the set of conditional values, which is a normal which can be seen as any other normal evaluator. We implement this by implementing a normal worklist based algorithm where we try to resolve the conditional values and try to handle mutual recursions also in that way, in this conditional values evaluator. And as we see that we have now a tagged conditional values, we have a conditional value evaluator. When we supply this tagged conditional value to this conditional value evaluator, we can get a final partial result, which is the evaluated conditional values. If you remember, in partial evaluation, we had a specialized program and an interpreter, which we used to specialize and get a specialized interpreter. Here also, in similar way, we have an evaluator. We have a specialized conditional value. What we propose next is a set of AM projections, where we say that we can specialize this conditional value evaluator in the same way how partial evaluation was specializing, how the first Utamura projection was specializing the interpreters for a particular program. Here we take the conditional value evaluator for a particular analysis psi, and the set of specialized conditional values, gm of x, sx, and get a specialized conditional values for that particular program element. This generated specialized C eval psi can now directly be put in the runtime, and where it can take the remaining runtime inputs and give you the final analysis result. For the specialized conditional value, what we got earlier, we can see this will be the partial result evaluator, where it should be able to take the remaining runtime inputs. If you can see here, we are taking first dependence as x1 and second dependence as x2, and then finally taking a mean for this analysis and generating the results. So this is how a evaluator can be generated for a partial result generated statically. And this can be placed in any VM to obtain the final analysis result for a particular element. So till now, what I explained, the set of conditional values and the evaluator which was generated was for a particular program element. We all know that we have several program elements present in a particular program. We don't want to regenerate the evaluators again and again for a particular program element. Instead of that, what we can do is we can efficiently generate the conditional value evaluators or the specialized conditional value evaluators by proposing a higher level of projection. So if you see here, we have the second AM projection, which says that when we specialize mix with the conditional value evaluator psi, we can get a specialized mix for that particular analysis psi, which can take a set of conditional values and can give you a partial result evaluator for each program element in a much more efficient way. Furthermore, similar to as how partial evaluation was giving me the Utamura projection was there for the higher level of projections, we can have third AM projection, which can give you a specialized mix itself, which can take any evaluator for a particular analysis psi. Since we can have multiple analysis being performed, we normally perform various analysis. So we can have evaluators for various analysis. So to generate in a much more efficient way, we can have this third projection as well. Now coming to the efficiency and correctness and precision of staging. In the paper, we propose several lemmas and theorems, where the first important lemma we say is that if the set of statically available dependencies is empty, then the specialization performed by first AM projection for a conditional value evaluator can be seen in the same light as the specialization performed by first few terminal projection, which means that how we were performing the specializations in partial evaluation, how we were performing the specialization, that we can see in the same way if we evaluate all conditional values. If we don't have any statically available conditional values, we can see in the same way how partial evaluation evaluates the program. Partial evaluation specializes the program. This is the first lemma. Second lemma says that since partial evaluation of a program with statically available inputs says that program is being specialized to the extent possible. That is the maximal specialization. So we can also say that if we evaluate all conditional values statically, then we are also specializing at a maximal level. Based on these two lemmas and properties, we propose the first theorem, which talks about the efficiency, which says that for a given program element and its statically available dependencies, the partial result evaluator obtained by first AM projection is maximal in terms of the conditional value evaluation that can be performed statically. So this says that when we perform partial analysis in a staged manner, you can perform maximal conditional value evaluation which can be performed. So this way we say that we are not leaving behind any conditional values that need to be resolved, that can be resolved statically, but we are leaving it out. The second theorem is about precision and correctness. Here we say that for any program element, the analysis result generated by whole program analysis and by the corresponding stage analysis are same. As partial evaluation says that if you specialize a program with the statically available input and then further supply the runtime values and further evaluate with the runtime values at the runtime, you will get the same result. In the same way, we say that if we statically resolve as much as conditional value we can resolve and then leave some for the runtime, we will get the same result. So in a way, we get the same result what we expect from a whole program analysis. So this is our theorem 2, which proves the precision and correctness for the staging model. For the future directions, we further talk in our paper the runtime features of Java-like languages, like we have reflections. So what happens when we have reflections that can occur at runtime? How do you handle staged analysis? How can you recover from if some dynamic features occurs at the runtime? For that, we use a separate analysis like control flow analysis, and we tell that if features like reflection happens, instead of just discarding the static analysis, you can have a fallback values as well, where you can, when some dynamic features happens, you can fall back to those options. We further talk about the cross-pollination of specialization idea as well in the paper. And also we talk about some of the other ways of performing analysis like query-driven analysis and feedback-driven analysis, where in query-driven analysis, we say that like whatever you want to compute, that much only you need. So can we generate statically in a staged manner whatever is required at the runtime? That much only should be required. Similarly, we discussed about the feedback-driven analysis as well. You can see this in our paper for further discussion. In conclusion, in this paper, we talked about how to formalize the theory of stage static plus dynamic partial analysis based on the theory of partial evaluation. We further gave projections for efficiently generating the evaluators and their generators for partial results. We proved the correctness and precision of stage static plus dynamic analysis so that it can be used anywhere in the VM. We hope from this paper that that after proving the theory for partial analysis, more partial analysis can be used not only for Java but beyond Java as well. Thank you.
Questions? Okay, so I had some comment about your theorem 2 in the slides, two slides before. So what does it mean that the results are the same? What is same here?
So basically what we want to say that, like, if somebody can ask, no, like whether the way you are generating stage program, you are performing stage program analysis. So the results will be same how you perform the whole program analysis. When you have the complete program available, will the results when you perform stage analysis will be same as what we get from whole program analysis.
What does result mean in this case?
The program analysis results.
Program analysis.
Suppose you are performing scape analysis, the status of a particular object, what is whether it escapes or not. That is the program analysis results.
Okay, okay. And like all the people, they are doing this kind of analysis. Do you think there's also any scope of putting some learning here, data-driven methods, or all these handcrafted heuristics or analysis enough?
So you mean by machine learning?
Yeah.
We really, since we want to be 100% correct, so there are possibilities that when our machine learning approach can go wrong.
But what would be the consequences of it going wrong on the end-to-end?
We might not have the reason why it went wrong. Like we might not able to guess why it went wrong, and we might not be able to have some fallback options. Maybe we have really not thought of applying machine learning in this, but
okay, thank you. Any other? Yeah.
Yeah, thank you for the talk. Have you quantified how much performance do you gain at runtime for the JIT analysis thanks to the static analysis?
So that was not our focus of our work. That was already given in 2019, the paper which I was talking about. In that, they show that like we cannot perform whole program analysis at the runtime. So it's practically infeasible to do a whole program analysis at the runtime. But for a bigger program, bigger benchmarks as well, they were able to terminate when they are doing this JIT analysis. So overall, it was the like whether you cannot perform and now you are able to perform for big programs as well.
Okay. Thank you.
Yeah, I would still say that, like, I mean, it's very impressive that, I mean, this theorem 2 is impressive. But still, I was thinking if there is some trade-off between being unsound and like the end-to-end performance of the code that you generate. If you are not like, if you want to like trade off, and ultimate goal, end-to-end goal is to get the fastest code available, then maybe you can be unsound as well.
Yeah, maybe.
I don't know, but thanks for the talk, and let's move on to the next.
Thank you.